For a very long time, humans have imagined what life might be like on other worlds. Thanks to the James Webb Space Telescope, the most powerful telescope in existence, that question can finally be answered. While observing the closest star system to us, Proxima Centauri, which is only 4 light-years away, scientists have noticed some peculiar anomalies from one of the planets in the system, Proxima b. These anomalies, called artificial lights, have puzzled the best minds in the scientific community. But what are they? Do these lights suggest the existence of intelligent life on the planet? Join us as we explore James Webb's terrifying discovery of city lights that change everything. The only life that we are currently aware of is on Earth. Since the beginning of civilization, people have questioned whether there is life elsewhere in the universe. To carry out such an interstellar search, American astronomers Jill Tarter and Thomas Pearson launched the search for extraterrestrial intelligence, SETI project in 1984. The nonprofit's objective is to gather spaceborne radio signals. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up the unique Allen Telescope Array in the Californian Cascade Mountains. This is because they are less dispersed or absorbed than other types of radiation. However, in the past 30 years, no verifiable alien signal has been discovered. Following that, the James Webb Space Telescope's successful launch aided in the quest to examine a range of distant, undiscovered planets orbiting far-off stars. The largest telescope in the world, which is floating roughly 1 million miles from Earth and outfitted with incredibly sensitive detectors, will be used. 20 years ago, there were no known signs of life on planets outside those in our solar system. Since then, more than 4,000 planets, also referred to as exoplanets, have been discovered orbiting other stars. According to NASA, the universe may contain trillions of exoplanets. The earliest signs of life beyond our solar system may be found in extraterrestrial plant life. The Galileo spacecraft turned its equipment back toward Earth when it was en route to Jupiter and found a definite indication of the presence of plants. The instrument detected the vegetation red edge VBI signature, a mix of red and infrared lights reflected by plants. For instance, a planet like Earth that is covered in a jungle should have a strong and easy-to-detect VBI signal. The JWST will measure the VBI of far-off Earth-like planets in the habitable zone around stars. These may be important signs of life in the exoplanet atmosphere. When sunlight crosses a planet's star, the JWST may be able to detect it as it enters the atmosphere. The light's missing wavelengths would then be discovered via spectroscopy. Atoms and molecules in the atmosphere absorb specific wavelengths, creating a characteristic fingerprint that the JWST can recognize. This method may be used to determine the composition of the atmosphere and assess where life is possible. It is likely that life could exist on Earth-sized planets with atmospheres similar to our own, with a predominance of oxygen, nitrogen, and carbon dioxide. By looking for elements that aren't usually present, one may be able to detect technological life. Chlorofluorocarbons, CFCs, generated for use in refrigeration and cleaning products, would probably be noticeable to aliens monitoring Earth's atmosphere from a distance. If the JWST found CFCs in planetary atmospheres, that would be a clear indication of civilization. However, life on exoplanets might not even remotely resemble life on Earth. Sometimes, even earthly life, like extremophile species, can seem alien. This is a group of organisms, primarily bacteria, that can endure environments where other living things would perish. Some can withstand heat up to 250 degrees Fahrenheit, while others can survive in strong acids with pH levels below 3. Planets like Earth are more likely to support life than planets with severe temperatures or acidic conditions, so it could be a good idea to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. The classification for our Sun is a yellow G-type star. These stars are less common and typically have shorter lives than our universe's stars. The likelihood of studying planets orbiting around red dwarf stars, which are more frequent and have lower luminosities and temperatures than the Sun, is higher. There is more time for the formation of life and evolution to produce complex life forms because these stars have significantly longer lifespans. Around 40 light-years away from Earth, the TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It revolves around a calm red dwarf star with 7 Earth-sized rocky planets. 3 of the rocky planets in the so-called habitable zone might have liquid water on their surfaces. The TRAPPIST-1 system, despite having a much smaller and colder mass than our Sun, radiates light similar to that of Earth due to the close orbit of its planets. The best chance for humans to see city lights outside the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Our nearest star, Proxima, is about 600 times fainter than the Sun, so a planet must be 20 times closer to it than Earth is to the Sun in order for it to support life based on liquid water. In August 2016, astronomers discovered a planet with 1.3 times the mass of Earth in the habitable region, a so-called Goldilocks zone, where the light intensity is just right to allow liquid water. Proxima b circles Proxima Centauri. It's possible that Proxima b is an airless, lifeless planet given that it orbits its red dwarf star at a distance of only 46 million miles. For context, the distance between the Sun and Earth is 93 million miles. Proxima b's close orbit exposes it to strong solar winds that can completely destroy its atmosphere. Yet it provides enough sunlight for temperatures and liquid water that are similar to those on Earth. Because of its close proximity to the star, Proxima b is thought to be tidally locked, always showing the same side to the star as the Moon does in reference to Earth. Proxima Centauri is about 18% the mass of the Sun and burns far less brightly than one might anticipate for a planet so near to its star, just 5% of the Sun's brightness. One might expect it to be a red-hot cinder, but liquid water could easily exist on Proxima b as long as the planet has an atmosphere to hold heat in, since the total energy reaching it from the Sun is only 65% of what Earth receives. However, the planet is not especially friendly to life. It is most likely tidally locked, which means it always faces the same direction toward the star, producing permanent day and night sides with significant temperature changes. Proxima b also receives 100 times as much high-energy radiation as Earth does because of its proximity to Proxima Centauri, including X-rays and ultraviolet light. It is bombarded with high-energy particles during star flare-ups. Unless it has a shielding magnetic field similar to Earth's, it is at risk. However, there are certain realistic conditions that could make it a pleasant world. Models suggest that the atmosphere of tidally locked planets may be susceptible to a rapid collapse due to the freezing out of volatile gases on the night side. Our planet's atmosphere can be replenished by volcanic activity, and for planets with strong magnetic fields, this atmosphere is less likely to escape. Because we don't know anything about Proxima b's volcanic activity or magnetic field strength, we can't even guess whether or not the planet has an atmosphere. But since an atmosphere presupposes the existence of seas, and the two taken together presuppose the existence of life, we are desperate to know if Proxima b has a sophisticated civilization. It might have solar panels covering the day side to generate electricity to light and warm the night side, which would otherwise be too cold and dark for comfortable habitation. The discovery of Proxima b has triggered a race to determine if it crosses its star's face as seen from Earth. These transits would allow scientists to determine the planet's size and mass, which would then enable them to calculate its density. Knowing the density would validate the planet's rocky makeup and provide information on the materials used to create those rocks. During a transit, starlight might pass through the planet's atmosphere, potentially disclosing its nature. However, the likelihood that the orbit will be in the right alignment for scientists to observe a transit is merely 1.5%. Additionally, the star's propensity to flare complicates matters. Astronomer David Kipping of Columbia University says the star is tricky, as stellar heat causes a rocky planet to absorb sunlight and re-emit it as infrared light. However, rocky planets produce a distinct type of infrared radiation from stars like Proxima Centauri. Additionally, the James Webb Space Telescope was created specifically to study infrared light. Proxima b's infrared heat signature is the key to identifying the planet's atmosphere. The infrared portion of the spectrum has a strong affinity for Hubble's successor. Possibly permanently, the James Webb Space Telescope will be able to observe city lights on Proxima b's night side, even if they were as faint as what our civilization currently employs on the night side of Earth. The Webb could detect artificial illumination as long as it was constrained to a frequency band that is 1,000 times narrower than the starlight. Proxima B's day side is heavily coated with solar panels because of its unique spectral edge's ability to reflect starlight. As Proxima B revolves around its star, day and night are identical. Cool evening lows follow daytime highs. The difference in temperature between day and night, however, depends on whether or not the planet is entirely composed of bare rock. An atmosphere and ocean both conduct heat. In other words, if there is an atmosphere, Proxima B's dayside and nightside temperatures will differ more. In fact, since the dayside will radiate all of the energy it receives from Proxima Centauri as a black body, we can calculate the precise amount of black body radiation that should be present. The night side, on the other hand, will look like a frozen form of hell. If the temperature difference between day and night is less pronounced, we can infer the presence of an atmosphere. Conveniently, it will only take the JWST 112 Earth days to measure the radiation from Proxima B's two faces after it has successfully completed its orbit around the star. In the event that Proxima B has an atmosphere, the next step will be to analyze its makeup. The presence of gases like oxygen, water vapor, and methane in particular could indicate the existence of habitable circumstances, if not actual living things. To accomplish this, however, we must successfully capture starlight as it bounces off or travels through the planet's atmosphere, which is a very difficult task. However, Webb can only closely examine a few of the closest potentially habitable worlds because it was not built to look for extraterrestrial life. Additionally, it is limited to tracking changes in the atmospheric concentrations of methane, carbon dioxide, and water vapor. Webb is unable to detect the presence of unbonded oxygen, which is the strongest sign of life. Even if some mixtures of these gases may be suggestive of life, one of the planned ground-based observatories that will be able to conduct a thorough atmospheric investigation is the extremely large telescope, which is scheduled to begin operation in the middle of the 2020s. Ozone may be among the substances that the JWST is capable of detecting. Until those telescopes are operational, the JWST may provide information that we can consider for a decade in the future. Even more powerful space telescopes may employ cutting-edge techniques to conceal the blinding brilliance of a planet's host star and reveal starlight reflected back from the planet. Consider doing something akin to covering the lights with your hand to improve your ability to see distant objects. Future space telescopes might do this by using small internal masks or large outside umbrella-shaped satellites. After starlight is blocked, studying light reflecting off a planet is much easier. Unfortunately, the majority of gases produced by terrestrial life can also be produced by non-biological factors. Methane is a gas that both cows and volcanoes release. Sunlight does this as well, converting water molecules into oxygen and hydrogen through photosynthesis. When searching for alien life, astronomers are sure to come across some false positives. Astronomers must have a thorough understanding of a planet of interest in order to assess if its geologic or atmospheric processes potentially resemble a biosignature and help rule out false positives. The next wave of exoplanet research may produce the compelling evidence required to establish the reality of life. The James Webb Space Telescope's preliminary data gives us a preview of the significant advancements to come. If there is life elsewhere in the cosmos, it is one of science's most pressing questions. It's possible that life is abundant throughout the cosmos, or it's also possible that we are completely alone, trapped on a solitary planet in deep space. In either scenario, significant philosophical and psychological adjustments among people will likely be necessary for the eventual resolution. The quest to understand extraterrestrial life not only inspires scientific exploration but also poses profound questions about humanity's place in the universe. As technology advances, the ability to detect signs of life in the cosmos becomes increasingly sophisticated. The James Webb Space Telescope, JWST, is a prime example of this progress, allowing scientists to peer deeper into space than ever before. Its ability to analyze distant exoplanet atmospheres offers a glimpse into worlds that may host life forms unlike anything we have seen on Earth. One area of focus is the concept of biosignatures, indicators that could suggest the presence of life. While traditional searches have prioritized oxygen and methane as prime biosignatures, researchers are also exploring a wider range of gases and chemical compounds. This broader perspective includes considering atmospheric phenomena that might occur due to biological processes. For instance, the simultaneous presence of certain gases, such as oxygen and methane, could indicate an active biosphere. Astrobiology is a field dedicated to studying the origins, evolution, and potential distribution of life throughout the universe. Scientists in this discipline investigate extreme environments on Earth, such as hydrothermal vents and acidic lakes, to understand how life can thrive under harsh conditions. This research helps inform the search for life on other planets, especially those with extreme climates that might have previously been dismissed as uninhabitable. Another exciting avenue of research is the study of ocean worlds, such as Europa and Enceladus. These icy moons of Jupiter and Saturn possess subsurface oceans beneath thick layers of ice. The potential for hydrothermal activity on the ocean floor raises the possibility of complex ecosystems existing in these hidden depths. Future missions aimed at exploring these moons could provide critical insights into the conditions that foster life. In addition to exploring our own solar system, exoplanets in other star systems remain a significant area of interest. The diversity of planetary systems discovered so far challenges previous assumptions about where life might thrive. Some researchers theorize that gas giants with dense atmospheres could harbor floating organisms, while rocky planets with extreme climates may host life forms adapted to their environments. The search for extraterrestrial intelligence, SETI, also continues, employing advanced algorithms and machine learning techniques to sift through vast amounts of data for potential signals from intelligent civilizations. This endeavor raises ethical and philosophical questions. If we were to discover intelligent life, how would that reshape our understanding of existence? Public interest in the search for life beyond Earth remains high. Documentaries, books, and even films contribute to a growing narrative that emphasizes humanity's quest for knowledge and connection with the cosmos. As we stand on the brink of new discoveries, the possibility of finding life beyond our planet ignites imaginations and encourages collaboration across scientific disciplines. In summary, the exploration of life beyond Earth is an evolving field that integrates technology, biology, and philosophy. Each new discovery or technological advancement brings us closer to answering one of humanity's oldest questions. Are we alone in the universe? The implications of this quest extend far beyond science, prompting us to reflect on our own existence and the nature of life itself.